inverters before. The idea is that you see over here in this, for example, this in figure 45, you see an NMOS inverter's configuration. If the input voltage is high, as we've discussed in the previous videos, well, the output voltage drops, okay? Because the rationale is that increasing the input voltage or the gate voltage enhances the inversion layer, so your space charge density increases. This in turn increases your current ID, which is flowing through the load resistance RD. Okay, so your V naught, which is equal to, okay, V naught is equal to VDD minus ID RD decreases. Okay, so this is VDD minus ID RD. So as you are increasing your gate voltage, okay, gate voltage is your input voltage because you're applying the input at the gate. This is your gate terminal. As you're increasing the input voltage, the current is increasing. Okay, so due to the increase in the current, since VDD is constant, okay, whatever is your power supply, it's fixed. So as the current increases, your V naught is decreasing. So it's an inverter circuit. If your input decreases, the input decreases, the current decreases. When the current decreases, the current ID decreases, V naught increases. So this is an inverter circuit. That's what we have discussed previously. Okay. So as a switch in digital circuits and even in analog circuits, NMOS, this configuration is used. Okay. So for example, this RD, this could be a load, this could be an electromagnetic coil, whichever you want to switch. So the advantage is that these MOSFET switches are more reliable and they have more speed as compared to analog switches. So you see over here, the MOSFETs can also be used as switch in a wide switch in a wide variety of electronic applications. So the transistor switch provides an advantage over mechanical switches in both speed and reliability. Okay. So the transistor switch that is considered here is also an inverter. So you see, even you don't have any input current over here. The input current is zero. Okay, since you have an oxide between the metal gate and the semiconductor substrate interface. There's no input current. Okay, but even with no input current, you can switch very large currents through the load resistors RD. Okay, so and this can happen very fast. This switching is very fast with the MOSFETs. So this is a switch in transistor logic circuits or digital logic circuits. The other applications could be, I mean, that MOSFETs, if you might know, they can amplify small time-varying signals, and we have talked about the digital inverters like this configuration. So they can be used to execute various digital logic functions in the digital circuits. Okay, so the difference would be that this resistor RD would be an enhancement MOSFET load device. Okay, so instead of this resistance RD, you have another NMOS or a MOSFET transistor instead of the resistor RD. Okay, so everything on transistor logic is consists of MOSFETs, based on MOSFETs. Okay, you don't have thin film resistors or surface mounted devices. Everything is MOSFETs. Okay. So this figure 45 shows an N-channel enhancement MOSFET device. So this is an inverter circuit. So now the operation is as such that if Vi is less than the threshold voltage, the input voltage is less than threshold voltage, then you know the transistor is in cutoff. That means there is no drain current. There is no current that flows from drain to source. So there is no voltage drop across RD. And that means if there is no voltage drop, ID 0, the output is simply VDD. The output V naught reduces to VDD for no ID. So the output is VDD. Okay. So you see that when the transistor is switched off, the output is V naught. Okay. And so this happens when ID is 0, and also there is no power dissipation in the transistor. You see, the power dissipated is in the MOSFET device for the given VDS is a product of VDS and the current ID that is flowing from drain to source. Okay, so when there is no current, there is no power dissipation. So if your input voltage is greater than the threshold voltage, the transistor is on. So and initially it's based in the saturation region. Why we favor this condition is that You see, as a switch, it has to ensure that the current is constant regardless of VDS and other operating conditions of MOSFETs. You see, in the transistor IV characteristics, this ID is constant. Okay, so for switching applications, ID is in saturation region, but that is so long that for small VIs, if you keep on increasing VI, what happens is you go on increasing ID and your VDS decreases because this V naught is also VDS. Okay, so if you're going to decrease your VDS, then you see in the horizontal axis, even if you are in the saturation region, even if you are in this somewhere over here, the Q point is somewhere over here, you tend to drop back to non-sat region. You don't want to do that. So if you go on increasing, I mean, the Q point can be shifted to non-sat. So if you go on increasing the input voltage, your transistor might get itself, I mean, out of the saturation region, and the operation could be in the non-sat region. So in this region, you see this the ID is VDS dependent. Okay, so initially, as a switch, you need to keep the transistor biased in the saturation region. Okay. Now, so since VDS is supposed to be greater than the overdrive voltage, this is your saturation voltage, VDS sat. So that's given as VGS minus VDN. So as the input voltage increases, the drain to source voltage decreases. Okay, because this is the story. As your input voltage is increasing, as Vi is increasing, ID is increasing, so your V naught is decreasing, your VDS decreases, and then you shift from sat to non-sat. So the transistor eventually becomes biased in the non-saturation region. So when Vi is VDD, that's a large voltage, you will expect, of course, okay, if Vi becomes equal to VDD, then your output voltage drops to a small value. That means the transistor is in non-sat region. Okay, so transistor is biased in the non-sat region. The V naught reaches the minimum value, the drain current reaches the maximum value. So basically it's an inverter circuit. That's what we have discussed before. So for large Vi, you have small V naught. For small Vi, you have large V naught. So it's just a switching action, okay, which is being controlled by the gate voltage, which is the input voltage, okay, also the input voltage. So well, in the non-sat region, this current relationship, current voltage relationship, is for non-saturation region. And you see, in non-saturation region, if you recall, your current is dependent on VDS. In this case, V naught is your VDS. I mean, over here, it's V naught is VDS. Same thing, because the source is grounded. So V naught is VD, so you can write this as VDS as well, which is equal to VD. So the current is dependent on VDS. If you go on increasing Vi, you're going to bias your transistor in non-sat region, and then this is the current and voltage relationship that you are going to use to find the current. Okay, to find the current that flows from drain to source. So V naught is still equal to VDD minus VDD. All right, and that is equal to VDS over here. So you can see this is VDS is primarily your V naught, the same thing, and the input voltage is the gate voltage, okay, or VG or VGS, the same thing, because Vs is 0. This is the source is grounded. Okay, here's a design example. The objective is to design the size of a power MOSFET, okay, to meet the specifications of a particular switching application. The application is such that the load in the inverter circuit, which is shown in the figure below, consists of an electromagnetic coil that requires an electromagnet that requires a current of 0.5 amps. Okay, so the current requirement is 0.5 amps, and here you have an electromagnet as a load in place of RD. Okay, so that's when the transistor is turned on. Okay, so that is the case when Vi is greater than threshold voltage, that is 1 volts. So the effective load resistance varies between 8 to 10 depending on the temperature and the variables. All you have is a 10 volt power supply. Okay, so VDD is your fixed at 10 volts, and RD is a variable load between 8 and okay, RD is varying between 8 and 10 ohms. Current specification is there, that is fixed. This is between 8 and 10 ohms. So this gives so when the transistor is on, ID has to be 0.5 amps, and preferably this should happen in the saturation region. Okay, and you're given the transistor conduction parameter Kn prime as well. That's the Kn prime, that is 80 microamps per volt square. So uh, between 8 and 10 ohms, you can see that V naught is going to vary. This V naught is going to vary between, the minimum will be 5, the maximum will be 6. Okay, I mean, you can work this out from this relationship. So V naught is VDD minus RD. In this case, it becomes 10. VDD is 10. Then the requirement is that, like, when the transistor is on, the design requirement is as such that ID should be 0.5, and this can be either, this is either 10, or this is either 10, or this is 8 ohms. So in which case this is either 5 volts or it is 6 volts. So the minimum is 5, maximum is 6. Okay. So in order to keep the transistor in saturation region, we will require, in order to keep this in saturation region, we will require the minimum, or call it VDS sat, as 5 volts. Okay. Let's keep this at 5 volts, and for that 5 volts, let's determine what VGS is. In order to ensure, first of all, your input has to be greater than threshold, that's given, but then this also has to be greater than VDS sat. So so you see, all you need to determine is your VGS. I mean, this VGS minus VTN should be greater than, well, this is your VDS sat. Okay, so let's see this VDS sat over here, saturation. Your VDS should be greater than VDS sat. So whatever your VDS is over here should be greater than VDS sat. So we can have a constant current. ID is 0.5 amps. Okay. So this can be written as VGS is, well, that's what we have to determine, but you have VTN as 1 volt. So let's say if VGS is 5 volts, if we keep VGS as 5 volts and threshold voltage is given as 1, then this comes out to be 4, because 5 is the minimum. Okay, I mean, the V naught, depending on the variation in RD, 10 to 8 ohms, will have a minimum value of 5 ohms, minimum value of 5 volts, and maximum value of 6 volts. Okay, so the VDS sat should be at least greater than 5 volts. Okay, so for example, for a given threshold voltage of 1 volts, if you select the supply, VGS supply, as 5 volts, 5 minus 1 is 4, then that means the transistor is indeed biased in the saturation region, and you can go on to find the current ID using the IV characteristics of the saturation region. Okay. So you see, one solution is to bias the transistor in the saturation region so that the current is constant, that is independent of the load resistance. So the minimum VDS value is 5 volts. I mean, you understand this. You see, this is a variable load. RD is a variable load over here. So which is varying from 10 to 8 ohms, and so minimum is 5, maximum is 6. So VDS sat is given by VGS minus VT and the overdrive voltage. So if you bias the transistor at VGS, if this VGS, or let's call this VI, is 5 volts, then VGS minus VTN is 4 volts. So the transistor is always biased in the saturation region. So next you can use the IV characteristics, I mean, for a saturation region, to find out what the current is. Okay. So you have this VGS, and you have this threshold voltage as 1 volt from here, and you have this electrical conduction parameter 80 microamp per volt square. You can plug it over here. All you're left with is a dimensional parameter WL, and the requirement was 0.5 amps. So this gives you, this expression yields that it implies that W by L is 781, which is a large dimension. I mean, even for a narrow channel like 2 micrometers, it's large width. I mean, this will be equal to about a little less than about 1560 micrometers. I mean, for a very small channel length like 2 micrometers, you are talking about very large width requirement for the channel. Okay, so this brings us to the idea that the dimensions are huge, and it is a power MOSFET. But let's see how much power dissipation does this MOSFET require for such a construction. You see, the power dissipated in the MOSFET is the maximum power dissipated will be, okay, it will be ID max, maximum current multiplied by whatever is your VDS. Well, what is VDS max? Well, VDS max is your is 6, alright, is 6. So since this is variable, so VDS max minimum is 5, maximum is 6. So that is equal to, when transistor is on, the requirement is to have a constant current irrespective of the load. So 0.5 into 6 is 3 watts. So the power requirement is 3 watts. So we are talking of a power transistor, okay, with a large dimensions. So maximum power dissipation in a transistor occurs when the load resistance is 8, VDS is 6, so Pmax can be evaluated as such, 3 watts. So the comment is that we can see that we can switch a relatively large drain current with essentially no input current to a transistor. So the idea is that, I mean, from the point in time that when Vi or Vg is greater than Vt and the transistor is on, and the requirement was that you were supposed to keep the current at 0.5 amps, okay? I mean, the coil of electromagnet requires 0.5 amps when turned on. Effective load resistance might vary, so but this variation should not affect the current, okay? So you keep the MOSFET, the operation of MOSFET, to keep the current independent of load resistance. We kept the MOSFET operation in saturation region, okay? In order to keep this in saturation, the VDS over here should be greater than VDS sat, okay, which in turn is the overdrive voltage. So all you need to determine was what is VGS in order to ensure that it stays regardless of your uh, load resistance variable, okay, which is 8 to 10 ohms. This should be at least 5 volts. The saturation VDS sat should be at least 5 volts. So that transistor is always biased inside. So that's all the design requirement for inverter MOSFET. Okay, and you see you don't need any input current over here to switch a very large current. So once there's no input current in the MOSFET. Okay, there's an oxide over here. So or you can say the gate current is 0, which is the case. So you need at least a voltage greater than threshold voltage, and then again that is required to turn on the transistor. But to keep it in saturation region, VGS should be about 5 volts, which is given over here. Okay. Then the transistor will always be biased in the saturation region, always be biased. So that's the requirement. So with essentially no input current, you can switch a very large drain current. And again, the size of the transistor required is fairly large, which implies a power transistor is necessary. So if a transistor with a slightly different width to length ratio is available, then the applied VGS can be changed to meet the specifications. So that means, what it means is that you see when you change your VGS or the input voltage, um, what happens is that your output voltage changes. Okay. I mean, due to the change in VDS, your power is going to change. Okay, so you have to adjust it for that. So if the transistor is slightly different, the width to length ratio is available. Then the applied VGS can be changed to meet the specification. And meet the specification means the power specification. For this power and the given W to L ratio, well, they can be interchanged. So you have to find what VGS is that is required to meet such specifications. I mean, this VGS is required. What VGS is required to keep the transistor in saturation region? I mean, it's all the only thing that we were selecting to keep the transistor operation in saturation was VGS. Okay. So once VGS determined, you determine VDS. Okay, and then this VDS determines the power, maximum power that you have, and the power and the size defines the requirement for the power MOSFET. Okay, that's all.